So now we're going to talk about the Hopf theorem. Okay, so I told you a few classes ago that the degree is, is a homotopy invariance. So if you have two maps that go from two manifolds at the same degree that, are closed, compact, and oriented, then the degree is preserved by homotopies. But an interesting question is whether the degree is the only invariant of such maps up to homotopy. So if you have two such maps, whether the degree is the only thing that you need to know to determine whether they're homotopic or not. And in general, that's not true. But if the target is a sphere, then it is true. So that's the Hopf theorem. So sometimes people say it's the Hopf degree theorem because there are other theorems about, by Hopf, like the Poincaré-Hopf theorem. So the theorem says the following. So let X be an oriented, compact, and connected manifold with no boundary, so such that the boundary of X is empty, and let F and G be maps from a dimension n, so xn. So let F and G be smooth maps into Sn. Then F is homotopic to G if and only if the degree of F is equal to the degree of G. Okay? So, as I just said, it's very important that the target is a sphere. And it's going to be pretty obvious from the proof. I mean, the proof is very constructive. So you really need to be on the sphere. But the domain can be any manifold as long as it's compact, connected, and oriented. Okay? I mean, it needs to be oriented and compact for the degrees to be defined. And the key point is that it also needs to be connected for this result to hold. Okay, so because you can't define the degree of a map from a disconnected manifold, but then you don't have this result. And really, when you have a disconnected manifold, you have two manifolds. So, like the degree, you could say, what's the degree on each connected component? So, sometimes people say, a manifold by definition is connected. Otherwise, you'd say it's two manifolds. Okay, so that's the statement. Any questions about it? About the statement? And obviously, this direction here we already proved. So what we really need to prove is that if the degrees are the same, then F is homotopic to G. Okay, so we don't need to prove this implication. So we only need to prove this implication. Okay, so now I'm going to diverge a little bit from Guillemin and Pollack, and I'm going to do a different proof, which will be kind of an inspiration to what we'll do next time, which is a generalization of this result. So before I start the proof, let me just tell you what we're going to do next time. We'll basically look at maps from manifolds that are of higher dimensions than n into S. And there is a similar result. It can classify them up to homotopy, but using some topological invariant. That's not a degree, but it's a little bit harder. I might say a few words about that later today. I think I will, yeah, if I have time. But anyway, the proof, if you've read Guillemin and Pollack, it's going to be a little bit different. But it's the same. It has the same smell basically, but the proof is going to be a little bit different. So to compute the degree, we have to choose a regular value. So I'm gonna start the proof by choosing a regular value. And of course, you can choose a regular value for both functions at the same time. So we're gonna let y in Sn be a regular value of f and g. Okay? So now when you look at the preimage of f, preimage of y by f, and the preimage of y by g, these are going to be a collection of points with signs. So I'm going to call this q0 and q1. Okay, so q0 and q1 are zero-dimensional submanifolds of X. So q0 and q1 are zero-dimensional submanifolds. Oriented submanifolds. So that means it's a finite number of points with signs, plus or minus. And the sign is plus. Basically, that means you take the orientation that's given by x, and if you take the sign minus, the minus sign, that means that the orientation of the tangent space that you want at that point is the opposite of the orientation of x. Okay, remember, we talked about what it means to orient zero-dimensional manifolds. That's actually pretty important. Okay, and remember that the degree of f is basically the number of points in q0, and the degree of g is the number of points in q1. And when I say number of points, I mean the oriented count. So basically, just sum a bunch of plus ones and minus ones. So this number here really, you should think of it as, it's not counting all the points, but it's counting the points with signs. So I'm going to use this sign because it's a little easier. But this really means, this thing means a sign count. Okay. So, so we need to show, so the way that we're going to do this, the way that the proof goes is, we're going to construct a homotopy of two different functions, an f tilde and a g tilde, that have the same submanifolds q0 and q1. So sort of the first step. So I guess there are going to be three steps. So the first one is to construct a homotopy from two other functions, f tilde and g tilde, such that basically the preimage of y by f tilde is q0 and g tilde is q1. So basically I'm going to replace f and g by two other functions that have the same zero-dimensional submanifolds, that have the same preimage of y. And that by construction they'll be homotopic. And then the second step, so there are only two steps. And then the second step step 2, I'll show that f is homotopic to f0, f tilde, and g is homotopic to g tilde. Okay? Okay, so basically what I'm saying is the information that I want to care about, are these points. I mean, it's actually just the degree, as you'll see. But I'll need these two to be equal. So if I take these points, q0 and q1, and I forget about f and g, the first step will be to use these points to construct a homotopy between two different functions, but that now have the same preimage of y. Okay, so then, by this construction, F tilde is homotopic to G tilde, kind of by construction, as you'll see. And in the second step, I'll show you that, because of this property, that's enough. This property for F tilde and this property for G tilde, that's enough to show that they're homotopic to the original guys, that they are a good replacement indeed. Okay, so that's the map ahead of us. Okay, so now let's do these steps. So step 1. Okay, so I have Q0 and Q1, which are finite sets of points in X. They have the same number of points. Well, it's not exactly the same number, but the same number with signs. So what we're going to do now is we're going to construct, let's C be a 1 manifold in an oriented. So we're going to construct an oriented 1 manifold in the product of 0, 1 with X such that the boundary of C is 1 times Q1 minus 0 times Q0. Okay, so let me draw a picture to explain kind of what I'm saying. So I know that Q0 and Q1 are a bunch of points in X. So I want to think of Q0 as being a bunch of points on 0 times X. And these points have signs. So say this point is a plus. Let me use colors. This is a plus. This is a minus. And this is a plus. And so this is Q0. And Q1, say, is just a point with a plus. So what I want to do is I want to connect these points in the following way. So say, for example, if I have this example, I can do this. And then here I can do this. So, what exactly am I doing? You can think of Q0, as being a list of points, and Q1 as being a list of points. So you can, for example, you can put the positive ones first, and then you kind of match like this. And at some point, you exhaust the positive ones of, you can map all the positive ones that you can. You can map all the negative ones that you can. And then at some point, you're going to be left with pluses and minuses on one side or pluses and minuses on the other side. And then you just kind of match them like this. Okay? So, we can construct these smooth paths inside the manifold. And then when you have the smooth path inside the manifold, it's pretty easy to actually get an embedded curve. You can just use the time t. You can kind of, these paths are, originally maps from 0, 1 to x. And then these give rise to a map gamma, a t gamma of t. If they're connecting Q0 to Q1, then this path here will be sort of this path, like this. But if you have a path that's connecting 2 points in Q0, then you don't want to do this one. You want to do something like, I don't know, t times 1 minus t and then gamma of t. Something like that. Because you want it to go from 0 all the way to, say, t1 half, and then to come back to t equals 1. So something like this. And the point really is, and then there's this other thing about the orientation. So basically, by choosing it this way, so for the pluses, you go this way. For the minuses, you go this way. And if you have, a loop within that starts and ends at Q0 or starts and ends at Q1, then you have to be, you have to orient it in the way that basically what you want is you want the orientation of the points that's induced by C to match on Q1 and to be the opposite on Q0. And you can see that you can find such a manifold, such a 1 manifold, exactly when the degrees are the same. So this condition is kind of, if you can find such a C, then basically the number of points here has to be equal to the number of points here with orientations. Because the total number of points on the boundary has to be 0. But then conversely, that's kind of what I was trying to explain here. If you have the same degree, then you can construct a one manifold like that. Okay, so is that clear? That you can construct this one manifold satisfying this condition. That's kind of the stepping stone of this proof. And now using this curve C, then we're going to build a homotopy. Okay. I see some quiet, confused faces. Are you confused or are you just taking it in? Yeah, fala. Não, não pode sobrar ponto. Yeah, so that's where we use this condition here, that the degrees are the same. So the number of points is the same up to signs, up to counting with signs. So there cannot be any points left. Exactly when the degrees are equal. So that condition is equivalent to the degrees being equal. Okay. So you do that. And now we're going to use a version of the tubular neighborhood theorem. So what we're going to do now is we're going to construct a map that goes from C times Rn into an embedding, actually, into 0, 1 times x. That's basically, like thickening. What we want to do is we want to thicken this curve. So, and I think of Rn as a really small neighborhood here. A little small neighborhood is diffeomorphic to Rn. So I want to thicken it like this. Well, you can always do this. This is like a kind of a simple theorem, but you can actually do this in a very specific way here. And the specific way that you can do is basically you can make sure that whatever basis, if you choose a basis of your vector field Rn here, of this tangent space here, that coincides with the derivative of this phi in that direction. So we construct an embedding. So we define an embedding like that with the following property. So we want that, of course, phi of x0 is equal to x. So we kind of take the core of the curve to itself. But then we want d phi, dv, say this is x and v. So when I looked at derivative at v for x0, so if I'm on here, I want this to be a specified basis that I choose here. And then a specified basis that I choose there. So I kind of, on the boundary of C, I want to fix this matrix. So that's exactly the matrix, that's kind of what happens at 0 when I take, that's what happens at 0, on this curve when I, that's the basis that's going to give this guy. So, one way to construct this, so I want to specify this. So I'm going to say a few words about this later. But why can we even do this if we specify that? That's because, we can look at this normal vector field. And the normal vector field to this curve, we can think of it, for these curves that start from 0 and go all the way to 1, the normal vector field, we can assume, the normal vector space is basically a copy of the tangent space. Of the tangent space of x. So because of that, and then now you use the fact that these curves like that, they have the same orientation. They start from a point with an orientation, they end with a point with another orientation. So if I have a given positive orientation here, I can take that, and through a homotopy, I can take this orientation, which you can think of as a choice of basis. You can take a fixed basis here and take to a fixed basis there. So like choosing a basis is the same as choosing an isomorphism with Rn. So you can kind of start with like for each curve that goes from 0 times x to 1 times x, you can choose like a homotopy of a basis. And either a positive basis if it's a positive point connecting to a positive point, or a negative basis if it's a negative point connecting to a negative point. So that's the first step. And once you have a choice of bases along the path, then you can just use the exponential map from Riemann geometry. And the exponential map will give you this embedding of this guy into here. I don't know if everybody knows the exponential map. But the exponential map is just what happens when you take the geodesic. So if you don't know about exponential maps, you can just kind of take, if you think about all your manifolds as embedded into some Rn for a very large n, and you have some tangent space there, you can just take sort of x plus tv for t really small. And that will give you a map of like from xv into, your Rn, like R x plus tv. So if this would be, if this is in some manifold and it is in some normal bundle, this will give you an embedding into some big Rn. So I mean that's kind of one way to prove the tubular neighborhood theorem if you have an embedded manifold, and if you don't want to talk about geodesics. But there's a way to do this intrinsically, which uses geodesics. So basically, if you have a point. If you have, you just want to x plus v, actually. And if you have a point, and you have a direction that's normal, you can look at the geodesic flow for time t. You can look at the geodesic flow at time 1 for that vector. And if the norm of the vector is sufficiently small, then you can always do that. So basically, you can rescale so that you can get an embedding of all of Rn. OK, so anyway, that's what you can do. Yeah. Yeah. So very, very good point. So that's another thing you have to do. So I said how you can specify how this works here. Like if you take a positive basis here and a positive basis here, you can connect them. And the same thing for negative and negative. But if you're going like this, then it's a little trickier. But it's still possible to connect a positive basis to a negative basis by a loop like this. So this is a kind of a topology exercise here to see that actually when you look at the normal space here, and you identify with the tangent space, and when you go along this curve, the normal space identifies with the tangent space here, but with the opposite orientation. So that's why this works too. So for these kinds of curves that go and come back to the same, side, then you can do that if the two bases that you choose have the opposite orientation, which they do because of how we chose the curve. So that's why we really need the degrees to be the same. And if the degrees are the same, then we can actually construct this thing. So we construct the curve C, and then if we want, maybe it's better to first, before you construct the embedding, you construct a path of bases along the normal of this curve. So you construct a path or a map that goes from the normal bundle of C well, okay, let me not write this. Let's just think about the embedding the way I said. You kind of construct. The idea is for a fixed basis here and a fixed basis here, you can find a homotopy of frames of the normal bundle. So that means it's a basis at every point that goes from here to there, and it also works from here to here. And the point is that it coincides with a given with a given basis that's oriented according to the orientation of the points. So you can do that for any choice of an oriented basis for each of these points. And the thing I want to do is I want to choose that. So let me write this again. So this is for every point in C. And then I want this, so the derivative at xv to coincide with, so I have already a nice, basically I already have a chosen basis here, which comes from the functions f and g. So, I already have sort of df at x, and I have dg at x. So, if x if x is equal to 1 times q1, if x belongs to 1 times q1, then I would like to coincide with the fixed basis on g. So it's my derivative. Okay, so, so actually, okay, let me not write this down yet. Let me just say that this is specified, and I'm going to specify it later, because I want you to understand what I'm doing and not write down a bunch of stuff. Okay, but it's specified, and I'll come back to this. But anyway, so once you have this, how do you define a homotopy? So what's a homotopy? A homotopy, is a map that goes from 0, 1 times x to Sn. So I want to define a map that is equal to y exactly on these curves. Okay, so that's what I want to do. So I want to define a map such that h1 inverse of y is equal to c. So that's kind of my goal. So what will I do? I'm going to use something very nice called stereographic projection. And that's why, we actually have to be on Sn. So I'm going to define, psi, which is the stereographic projection, from Sn minus, and I remove negative y, and take this to Rn. And this is the stereographic projection. And the stereographic projection is very nice. And in particular, if I define the stereographic projection with, this, so I have my y, and I have my negative y. So what I do is I take a plane that goes through y, and I project like this. Okay, so that, in particular, the stereographic projection, so it's a diffeomorphism. And psi of y equals 0. Okay, so that's kind of what I'm going to need. Okay, so now, basically, I want to tell you that using these tubes around the curve, I can define my homotopy H. So how do you do it? Well, if you, so H is defined like this. So 0, 1 to Sn. So if you take a point that's in the image of this diffeomorphism, phi of xv, basically the idea is I want to just take this to v. But then I look at the stereographic projection, that's going to give me a point in Sn. So of a point of this form, I want to take this to, maybe let me write this like this. So h of x, h of u. So this, I would like it to basically to be v if u is phi of xv. But v is a point in Rn. So I'm going to use the stereographic projection to map it to Sn. So psi inverse of v. So basically what I'm doing is like for each slice here, I'm mapping it to Rn, which I'm mapping to Sn. And then I map everything else to negative y if u doesn't belong to the image of phi. So basically, this homotopy is just built from the stereographic projection. So kind of each slice here, you map to Rn. But then as you get close to the end of the slice, to kind of the infinity of Rn, then everything is converging to minus y. And then everything that's on the exterior of these tubes, you map to minus y. Okay, so that's the map. Uh-huh. Menos y. Uh-huh. Yeah, so I mean, it's not hard to see this map is continuous. I think it's kind of clear, because as you go towards the, the infinity, so your Rn is just contained in here. It's like an open disk, if you want. But, it is Rn because as you get closer to the boundary of this disk, basically you're going to the infinity in Rn. So then you're going to this point here, minus y. Okay? So maybe this is the most important idea of the proof. So I want to take some time for you to digest. I'm going to say the same thing a few times. So basically every slice here, you're mapping it based. You're thinking of this tube, and if you're inside the tube, you have a copy. You are at some point on the curve, and then you're in some point in Rn, and you just want to take that point in Rn, and then you map it to the sphere using the stereographic projection. And the further you go out, the closer you're getting to the top of this minus y, which is like acting as the North Pole. Okay? And then outside of these tubes, you just map everything to minus y. Okay. So that's the map H. And it's actually quite simple. It's like surprisingly simple. But what you can check, is, and now, you can define, I guess I can say this is an exercise. H is smooth. Y is a regular value of H. And the preimage of Y is just equal to C. Now, if you restrict H to the boundary, then you have two functions from X to Sn. And those are the two functions that I'm going to call F tilde and G tilde. So now you define. So these are not very hard. Maybe the smoothness is the most subtle one. To see that like on this actual boundary, when you reach minus y, they have a smooth function. Okay, so that's maybe a slight detail, but it's not so hard. Maybe you can do that by taking the opposite. No, I don't know. Anyway, you can do the exercise. Showing that y is a regular value is very easy because the stereographic projection is a diffeomorphism, and you have these properties here, and I still need to specify what I want here. But in principle, you know that there exists some so far, you can just use any kind of embedding, any tubular neighborhood that you know exists. And then, you can define F tilde to be, F tilde is equal to H restricted to 0 times X, and G tilde is H restricted to 1 times X. To be honest, maybe I should write it like this. H of 0 dot and H of 1 dot. Okay? So, and then by construction, by construction, F tilde is homotopic to G tilde. I constructed a homotopy even before I constructed what it's a homotopy between. So they're homotopic. And then the other thing is that the preimage of y by F tilde is exactly the intersection of C with 0 times x, and the same thing for g tilde. So this is Q0, and this is Q1. Okay? And you have to be a little, careful, but actually these come with the right signs. So if you look at the pre-image of, because sort of the x has the opposite orientation when you look at it sort of as the 0 times x slice on the boundary, then that changes the signs from the boundary of C, and you actually get Q0, with the orientation that, it came from F. So, this is true as oriented manifolds, or as oriented points. Okay? Because I said, the boundary of C, these Q1 and Q0 appear, but then you have to change the signs of Q0. But then you kind of change it again when you look at this equality here. So then basically when you look at the pre-image of F tilde, maybe this is not a question for G tilde, but when you look at the pre-image of Y by F tilde, you get these points that are on the 0 times x slice, but then they come with exactly the signs that they were given before. So like in this particular picture here, for example, you'll still have the pre-image of, so F tilde is this function restricted here, and G tilde is the function restricted here, and when you take the pre-image of Y, you're going to get exactly the intersection of C with this slice. So these points, and they're supposed to come with a negative sign because of this, but you flip the sign because you define F tilde as the function like this. Okay? Is that clear? I know it's kind of a subtle point, the orientability, but apart from the orientability, is it clear what I just did? Yes, mais ou menos? I can say one more time. Okay. So you see, like the function that I built on these slices here, it's defined on basically on these slices that come from the normal bundle of this curve C. And it is an embedding. These slices, the normal bundle kind of embeds in here, and it's Y exactly at the 0 point. So that's why we have this property here. But if I look at the boundary of 0, 1 times x, that's the same as looking at the boundary of C. So F tilde is the restriction of H to this slice, and G tilde is the restriction of H to this slice. So I reach Y exactly at these points, which are the centers of these, I guess here a tori, but yeah, but in higher dimensions you just have a point times an Rn. Or a point times a little open ball if you want. I mean, it's convenient to do Rn just because of the stereographic projection, but you could have done it with an open disk. But then you need a function that kind of converges to the opposite point, the antipode of the center, when you get close to the boundary of the open disk. Okay. Anyway, so that's it. That's basically the first step. What I haven't told you exactly is how I want to choose this dy dv. And that's kind of going to come into the second step. So when the second step is to show that F is homotopic to F tilde, and G is homotopic to G tilde. Okay. So in order to do that, I'm going to actually be more careful about how I choose this embedding. And I actually want to choose this embedding so when I look at F, when I look at F of phi of xv, what I would like is that the derivative of this with respect to v at v equals 0 so I'd like this to be the identity, basically, on the boundary of C. So for the points, the points x of the form, so x on the boundary of C intersected with 0 times x. Okay, it's a little confusing, but oh, no, sorry, this is not the boundary of C. This phi sorry, this is a little confusing. My notes are not the best, but no, that's right. I want this derivative to be the identity yeah. Okay. So, sorry. Let me do this again. Sorry, I should have written better notes. So if x is in Q0, which Q0 you can think of as contained in the boundary of C, what I'd like to do is I want f of phi of x0, the derivative with respect to v. Yeah, that's what I want. To be the identity. Yeah. So, what's that saying? That's saying that if you, by the chain rule, this is going to be the derivative of f times d phi dv at x0. And I want that to be the identity. So, basically, I would like to choose phi so that I basically, the basis that I want to pick is the inverse of the derivative of f. So that's what I wanted to say earlier. But I didn't want to kind of scare you at that point. But, basically, if you look at the derivative of f, in coordinates, or, when you, after you push forward by, I guess, maybe you need to also apply phi to that. You have to look at the stereographic projection, and then you look at the derivative. Yeah, because this map, when you look at the stereographic projection composed with f, composed with phi, of dot 0, of x dot, that's a map from Rn to Rn. Yeah, that's what it is. Right? So if you fix a point, you think about your Q0, it's a bunch of points. So over here, I can look at basically this phi, and I can apply f to it, and then I can apply psi that will bring me to Rn. So what I'd like is this composition to basically the derivative of that to be the identity. Yes. Okay, so that's the point. No, forget about the 0. This phi, it actually the phi doesn't invert. The phi preserves the orientation by definition. No, so actually, I want the phi to take that into account. So yeah, sorry, the phi doesn't preserve the orientation. Phi preserves the orientation of the point. So if the point is positively oriented, then it will have the same orientation. Then if it's negatively oriented, then the phi is going to switch the orientation, because I basically want this to always be the identity. Okay, so I don't know. Is this a little clearer now? What I'm trying what I'm trying to choose. Okay, so the reason I want to, yeah, let me say this one more time. Oi? A phi vai inverter também, exatamente. Yeah. Yeah, porque, okay, because, x, if I take a point that's on Q0, so I'm going to do something for Q0, then I'll do the same thing for Q1. So if x is in Q0, then, I have that phi of x0. This is just mapped to the same point. So, this is just the same x, right? So then I can look at the derivative at that point. So the derivative of f at that point will be, a map from the tangent space of x to the tangent space of y of Sn. But when I use the derivative of phi, I can identify this with Rn. And when I use the derivative of the stereographic projection, I identify this with Rn. And the stereographic projection is orientation preserving by choice. And then I guess, this step here, is really kind of, this is kind of the condition that I'm requiring on phi. That it might be, so this is different from what I was doing earlier. So this phi might preserve and might change orientation. But the condition I actually want is the composition with phi, the derivative is the identity. So I actually want it to have the exact orientation that's given by the point. So if the point, it's orientation preserving with respect to the orientation of the point. So it'll match the orientation of the point. So, the condition that I want is that sort of phi composed with f composed with phi of x0, that the derivative of this with respect to v, so the derivative of this map at the point x0, this is the identity. Okay, so let me say this one more time. If you see your f and you compose it with the if you compose your f with the stereographic projection, maybe let me say this another way. That will give you a map from a neighborhood of your x to R, n. Okay? So you can look at the derivative of this map. So that's going to give you a map from Txx to Rn. So basically what I want is I want to choose the basis that comes from this derivative, or that will make this kind of the identity. Okay, so I want to find a chart, if you want, into Rn, so that the composition here is the identity. So that's, if you want, you can think of this as an embedding of Rn into this neighborhood. And that's the same as choosing a basis, you choose it for one point, and then by the inverse function theorem, you can assume it's the identity locally, if you want. Okay, but I think, I actually only need this assumption right here to say what I want to say. So what I want to say now, and this is the condition that we'll need to prove the homotopy, or to construct the homotopy, is that if you look at f of phi of xv, and you apply the stereographic projection, when you take the inner product with v, this is going to be positive for v, norm of v, sufficiently small. So that's the condition that we're going to need. And that's why it's kind of important to fix that basis at the origin for every x. Okay, and yeah, so this is not true for v equals 0, obviously, but the point is that this guy here can be approximated, by this derivative. So this guy here is you can write this guy as, this is going to go to 0 at v equals 0. So like by Taylor's series, this is going to be equal to v plus something that is of the order of v squared for a given x, for every x, as you vary v. So when you multiply by v, when you take the inner product with v, this is going to be norm of v squared plus the order of norm of v cubed. So that's why, if norm of v is sufficiently small, then this guy is quadratic. So it will be positive for v different from 0. So this is the condition that I want. And you see why this is important. Okay, so I do this on Q0, like for x on Q0. And I do the same thing for G for Q1. So basically, I do the same thing for G for x in Q1. So, maybe I should have said this slightly differently, but, the way that, you really want to do this, the way you want to construct this, this embedding, you can think of it the following way. So first you have your Q0, and you embed Rn into neighborhoods of these points, satisfying this condition. And you do the same thing for Q1. I'm going to use the same number of points as I had before, but using G now. And you do have to do this because, like, if you take the derivative, and if the derivative is kind of rotated with respect to kind of the Euclidean basis, then this condition is not going to be satisfied in general. And you see why this condition is kind of important. So you do that here, and you do that here for G, and then you can actually extend, as I told you earlier, with any given, like with bases that are compatible, then you can actually extend this to a framing of the normal bundle, so a choice of bases of every fiber of the normal bundle, which will give rise to this embedding. Okay, so then you have this property, and then now you can actually prove that f and f tilde are homotopic, and similarly that g and g tilde are homotopic. So now actually I don't care about this h anymore because here's my f tilde. I just care about f tilde. And then what I want to do is I want to show that I can build a homotopy to f. And f has the same points with the same signs, and even more, the same framing, which, this idea of framing will be clear maybe a little bit later. But the idea is, like, I choose this basis, which is the derivative of f in this chart. And now I'm going to construct a homotopy here. So let's see how we do that. So we can ignore G for the rest of the proof because we're just going to work with f and f tilde. And the same thing works for G and G tilde. So remember that the way that f tilde was defined. So basically what we, the way that f tilde was defined, f tilde was just defined as h of 0 dot. And by construction, basically, it satisfies this property because h of 0 dot is just, when you apply f tilde to phi of xv, that's just equal to psi of v. Okay, where psi is my stereographic projection. No. That's wrong. It's just, no, it's psi inverse of v. So there we go, yeah. So that means that after looking at the stereographic projection, I actually have just equal to V. So it's kind of what I was trying to say earlier. Like this map is just looking at Rn right in there. Okay, so I have this property for F tilde. And for F, it's not as good. Like for F, when I look in these coordinates, I have V plus some order, blah, 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 blah. But what I can do is I can do some brute force homotopy. Just kind of, homotoping one to the other. But it will only really work well in this ball of radius epsilon. So to do that, so I choose a bump function. A bump function. Rho that goes from, say, Rn to 0, such that the support of rho is contained in this ball of radius epsilon. So inside of this ball of radius epsilon, I'm going to do a homotopy, brute force homotopy from F to F tilde. Of course, with a stereographic projection in mind. So like once I put my stereographic glasses, then I see everything in Rn. So then I can do homotopies, like linear homotopies. So, and then I have to put this bump function to make things glued together. So now I can actually define the thing. So I can define, and I also, of course, I also like to have rho equal to 1 in a neighborhood of 0. So say in, I don't know, Bn of epsilon over 2. Something like that. So I have my bump function. And then I can define, well, let me go over here and define the homotopy. So if I'm inside this ball of radius epsilon over 2, I just really do the linear homotopy. So brute forcing means, I can take my psi composed with F composed with phi of xv. Well, let me just write it like this. Phi of z. I put a 1 minus t here, and then plus t times psi of F tilde of z. So I can do this thing. So this is if z is in the cylinder, in this phi of, if z is equal to x of xu. So I do this linear homotopy, and then I have to kind of I have to go back to Sn, and I have to put my bump function, because I actually can't go beyond the ball, as you'll see in a minute. I'll explain why you can't go outside of the ball of radius epsilon. You need that condition. So this, you put, basically, now I'm going to actually add this rho of u times t here, and then rho of u times t here. So basically, if you're inside this ball, this kind of small ball of radius epsilon over 2, then you really do your linear homotopy. If you're outside that ball, then you kind of do less and less homotopy. And then at the end, like when you're outside of this ball, you just have F. So this is a map that, this is my ft of z. I'm going to define to be this guy if I'm inside that cylinder. But here I'm only, so the ft is only really a homotopy from this guy. No, ft is just a map from x to Sn. So my cylinder now only really, it's not a cylinder anymore. I'm just kind of thickening it only on the 0. I'm only looking over here. So my x now is not on C anymore. My x is only on Q0. So like x is a point in Q0. This phi here, I'm just restricting it to 0 times x. So x is in Q0. Okay, so I do this, and then outside of this guy, I just say it's equal to f of x, f of z. Otherwise. And the point here, the reason that I make this super annoying choice, and I want this condition, is if this condition holds for the whole homotopy, then I'll guarantee that the only time I actually hit 0 is at the middle of the point, is for v equals 0. So the reason I have that condition is to guarantee that ft inverse of y is always equal to q0 for every t. Okay, so to guarantee that, in other words, this guy here is only 0 exactly for that original 0 point. Okay, so how do I do that? Basically, I remove the phi inverse because being equal to y is the same thing as being equal to 0 after the stereographic projection. And then I use the dot product here. I take this guy here and take the dot product with u. Oi? Vezes t? Yeah. So, I take this guy, and I take the inner product with u. I guess I use u instead of v, but, it's the same thing, u and v. And then, this guy here is going to be positive, and this guy here is just u, so times u is going to be positive, unless u is equal to 0. And that's exactly the point. Okay? So, yeah, so this is the first step. So basically, this builds a homotopy from, so this means that f is homotopic. So on one side, I have f, and on the other side, I don't have f tilde. I just have something that's equal to f tilde in a neighborhood of q, 0. So you see that, if you are inside that bump function part, so here's my q0, a bunch of points. So I have this ball of radius epsilon, I have this ball of radius epsilon over 2. So this homotopy goes between f and something that's equal to f tilde in this neighborhood. So it's f tilde, so the thing that it's homotopic to, so at time 1, this is homotopic to basically f tilde. But only inside this ball of radius epsilon over 2. Outside, it's some other thing. So, you can kind of call, if you want, you call this f double tilde. So f tilde tilde is this f1. Okay, so because I constructed a homotopy, then, of course, by construction, f is homotopic to f tilde tilde. So it remains to show that now I can actually, this f tilde tilde is homotopic to the f tilde. And now I actually kind of do the opposite construction, or kind of I look at because now I know that inside this guy, my f tilde tilde is equal to f tilde. And outside, I don't have any control. So now I'm going to kind of go on the outside and do a homotopy to get to f tilde. Okay, so basically, the rest is a very easy linear homotopy. So anyway, before I write this down, I think that this proof is a little bit confusing. And I'm going to try to re-explain it. And also, you should know that next time, we're going to do almost the same proof, but kind of in higher codimensions for the Pontryagin-Thom construction. So let me say again, I kind of want to stop, and I see some confused faces, so I kind of want to say, again, give you the map of what we're doing. So we had two functions, f and g, that had basically, the same number of, the pre-image of y was basically the same number of points with these multiplicities. So the first thing we did is we said, okay, we're going to construct, we look at the pre-image of y by f and g, and those are going to be two sets of points that have the same number, except that one of them might have more points with pluses and minuses. But if we kind of just concentrate on the easiest case, which is they're all positive and they have the same exact number. So then you actually say, now I'm going to construct a homotopy of maps that have the same property that the pre-image of y is Q0 and Q1, but are not F and G, are some other maps, but have the same pre-image. So this F tilde and this G tilde. And you kind of construct the homotopy and the maps all at the same time. Okay? And the way you do it is, like first you kind of choose a thickening of these points. So you choose an embedding of Rn here and here, and here and here. That's kind of compatible with the derivative of F and compatible with the derivative of G. And then you extend this thickening to the whole neighborhood. And now, this thickening is basically an embedding of a copy of Rn. And this Rn is really the map that you want to define to Sn, because Rn is Sn except for one point missing. So, this is how you define the homotopy, so the map to Sn. So each of these Rn's goes to the Rn that's embedded into Sn by the stereographic projection. And then on the complement of this, you define it to be minus y. But in particular, you've defined this F tilde and this D tilde exactly that way. So what I'm doing here, this part here is to show that this F tilde, I'm trying to show that this F tilde is homotopic to your original F. And what I did here is I did a step in between. So I homotoped F to something that is equal to F tilde in these neighborhoods. But outside of these neighborhoods, it could be something else. So this step here, I constructed some F tilde tilde that coincides with F tilde in this neighborhood. But outside of this neighborhood, it's something else. And it actually coincides with F outside of even bigger neighborhoods, but it doesn't really matter. Okay, so first I homotope F to something that's equal to F tilde just in a neighborhood of these points of Q0. And then the last step is to construct this homotopy right here between F double tilde and F tilde. And this is actually the easiest part, because if I'm outside here, I know that the function takes values away from y. So that F tilde and F double tilde are both functions into Sn that never get close to y. So then I can use the stereographic projection, but now the north pole I put at y. And then I can do a linear homotopy there too. So that's what we are going to do. And because they coincide here, we don't even need a bump function. So finally, we can define another homotopy. Let me call this, I don't know, HT. That's defined like this. So let's say that this neighborhood here is U. So my U is, if you want, it's phi of Q0 times this ball of radius epsilon over 2. Okay, so this kind of little neighborhood where I know this F tilde tilde is equal to F tilde. Where the support, where rho is equal to 1. Okay, so I define the homotopy like this. So HT of Z, this is going to be, I just do psi of F tilde tilde with a 1 minus T, and then plus T times psi of F tilde and psi inverse. So I do this thing. So I do the linear thing, but I have to put the stereographic projection. Oh, and sorry, this is not psi. It's a different stereographic projection. So I have to look at, I don't know, phi, which is the stereographic projection now about y and not about minus y. So kind of I flip the stereographic projection. Because now, if I want to be away from these neighborhoods. So if I'm away from this neighborhood, then I'm away from y. So I can use a different stereographic projection, not phi. I'm running out of sigma. And then I do the linear interpolation of sigma of f tilde of f double tilde of z plus t of sigma of f tilde of z. And then I do sigma inverse. So this is if z does not belong to you. And if z belongs to you, then I just set it to be f tilde of z if z belongs to you. But in u, f tilde and f double tilde are already the same. So this is why I don't even need a bump function. They actually glue nicely. So there you go. I basically get this homotopy too. Okay, so this one is actually harder to construct. Okay, so anyway, and this is the end of the proof. Okay, so let me say one more time, and I'm sorry for, it was a little confusing at points, but you have these two functions where the degree is the same. So you look at the pre-image, and you're going to have a bunch of points that are the same number of points up to these pluses or minuses. And then the first thing you do is you construct a homotopy where you kind of forget about the function. You just keep the set of points and the framing, which is kind of this basis, this fixed basis. So you just keep that, and you construct a homotopy of two other functions that have those fixed pre-images. And then the second step is to show that these functions they built by hand, they are homotopic to the original functions. And that step is a little bit more annoying, but you do it in kind of two sub-steps. One is you construct a homotopy near the pre-image of y, and then you construct a homotopy away from the pre-image of y. And in both cases, it's just linear, just a linear homotopy. When you see with your stereographic projection eyes. Okay? So anyway, that's the proof. Okay, are there questions? Now it's a good time to take a breath and see if you understand, if you have any questions. No questions? Okay, so now I'm going to start talking about a generalization of this theorem, which is called the Pontryagin-Thom construction. And to talk about that, I'll talk about what it means for manifolds to be framed, and then maybe this is even going to make more sense, potentially. That's my hope. So I'm going to talk about the Pontryagin Thom construction. Okay, so the idea is that we take an oriented xn, an oriented compact manifold connected. No, I don't actually need it to be connected. Yeah. And the goal is to classify maps from X to Sm up to homotopy. Okay, so I want some kind of invariant that will be preserved by homotopies, and it will tell me exactly when these maps are homotopic. Okay, so I know that if if n is equal to m and x is connected, then the degree will do it. But I want something that generalizes the degree. Okay, and that thing is going to be what's called framed cobordisms. Okay, so first of all, let me tell you what a framing is. So definition. I mean, and of course, I'm only really interested in the case n greater than or equal to m. If I have the other case, then if f is not surjective, then f is homotopic to a constant. It's not that. The other situation is not that interesting. Okay, so we want the dimension of n to be at least the dimension of m. The dimension of x to be at least the dimension of the sphere. Okay, so now let's talk about framings. So what's a framing? If we have a k-dimensional submanifold of x, say that Q is compact, unoriented, and compact manifold. Well, it doesn't actually have to be compact, but let's just say, well, any submanifold, really. So a framing is the following thing. A framing is a trivialization of the normal bundle. So that means, I know the normal bundle, the fibers of the normal bundle are all an Rn minus k. But a trivialization is a specific choice, a framing is a specific choice of an isomorphism, of a diffeomorphism of Q, of this to Q times Rn minus k. Okay, so that's what a framing is. And that's the same thing, saying, that I have an isomorphism. I choose an isomorphism of every normal space to Rn minus k. It's the same thing as saying that I choose a basis. Because I can just pick the Euclidean basis here, and that will give me a specified basis of the normal bundle. Okay? So, and remember what the normal bundle is. Like every submanifold has a normal bundle. It's just you pick a Riemannian metric, and then on the tangent space to x, you just take the orthogonal complement of the tangent space. Okay, so let's give some examples. I think this is maybe a slightly abstract notion. We can start with a knot. So say examples. Say you have a knot in R3. So, let's start with the easiest knot, which is this, the unknot. And what is a framing? So for each point, I have a normal space. So in this case, it's a plane. It's the plane that's perpendicular to the tangent of the knot. And a framing will be a choice of a basis for every point. So, basically, I can say, oh, this is my basis, V1, V2. So I have to choose a basis at every point. So that will give me, if I choose a basis at a basis for the normal space at every point of the knot, that will give me a isomorphism of the normal to the knot and k times R2. In fact, as I said, it's equivalent. It's equivalent to choose a trivialization and to choose a basis at every point of Q. Okay, so that's called the framing. And if you don't care about homotopy, I mean, in fact, actually, if everything's oriented, if you're not so oriented, then the normal bundle will be oriented, as I explained a few classes ago. And it's actually enough to choose one vector. Because if you choose one vector field that's along your knot, then the second one, you can just take the orthogonal complement so that it's a positive basis. So actually, if you want a framing on a knot in S3, all you need is one non-zero vector field that's normal to the knot. That will give you the desired framing. And it's very common, actually, like say I have this knot. It's very common to describe the framing by like another knot that goes around this knot, that's nearby this knot. So if say I want the V1 to always point up, I could say, well, just do a little exponential in that direction, and you get another knot like this. So then you have this this braid basically, that where this means that this is the knot. This refers to the knot, and this guy here refers to the framing. You see, this is a framed knot, so it's a knot with a specified choice of framing. Okay, but you could do something more interesting. Like you can take this knot, and you can take a framing that goes like this, where your V1 starts vertically, and then it kind of does a whole loop around this plane. It goes down, and then it goes up. Like if this is your unknot, you start with the V1 that goes like this, then it goes down, then it goes back up, and then it joins like this the other side. So it does a whole loop around this direction, the transverse direction to the knot. Okay, so then you could kind of, as a, if you just follow along, if you exponentiate this V1 a little bit, then you can kind of do something like this. And now you see that these two framings are actually different, and they're not even homotopic. So they're really different kinds of, they're really different framings. Because you could take your first frame, you say you start with this, V1 up and V2 like this, and you go like this. But then you could actually just change the two of them and go like this. And these two framings are homotopic, because there is you can go from one framing to the other framing with a family of framings. But that's not true for these two framings right here. Okay? So anyway, this is framings in knots. Framings on knots. That's just, yeah. And if you understand what I'm saying here, it's not very hard to see that every knot admits a framing. So every knot in S3 admits a framing. Because you can always find a non-vanishing vector field that's normal to the knot for every knot. So this is, maybe I should say this is an exercise. I think it's a nice exercise. And maybe the observation that I should do in general is that not every manifold, not every submanifold Q, K in Xn admits a framing. So it's not true that every manifold can be framed. Every submanifold can be framed. Because it's not true that the normal bundle is always trivial. Okay? So sometimes the normal bundle is trivial. And in these times, then it can talk about a specific choice of trivialization. Okay? And sometimes, like for example here, if you take a knot, then the normal bundle is trivial, is always trivial. So you can choose a specific trivialization. But the thing that's cool is like once you have a trivialization, then you can change the trivialization. So once you have a framing, you can change the framing. And for knots, that's very easy. Because a trivialization really is the identification of the normal bundle with S1 times R2. And you can choose another basis that's just given by, so in this identification, now you could say, how about I choose a vector field V that does like this. So V of t is equal to t and then e to the 2i, e to the it, e to the kit. Yeah, there we go. So this vector field, I'm writing this vector field in these coordinates here. So once I have a framing, I have an identification of the normal bundle with S1 times R2. And my S1, I'm thinking of as R times 2 pi z. So then I can choose another vector field, which, what does it do? So as I go around the knot, the vector field is turning. K times, because I put a K over there. So this is a new vector field, and if you take this vector field and its orthogonal complement, in a positive fashion, that will give me a new framing of the knot. Sort of the old framing would be if I just take the constant guy. So this is T and 1, 0. That corresponds to the old framing that's given by this. But once I have one framing, then I can change the framing by doing this. And an interesting exercise is that these are all different framings. They're not homotopic for different values of K. So actually, given a knot, there is a Z worth of framings. There's actually a notion. It's an affine space. You can compare two framings. There's a difference between two framings that's kind of given by this number K here, up to homotopy. OK, so that's framing. And what I want to tell you about is why this has to do with maps from X to Sn. So the thing is, if now we take a map from Xn to Sm, and A is a regular value, then the preimage of A is a submanifold. But the thing is, the preimage of A actually is a framed submanifold. So it inherits a natural framing. A natural framing from F. And how does that work? Well, we know that when you look at the normal, so the derivative of F, if we take a point on the preimage, so if X is a point on Q, which is the preimage of A, how do I get a framing? So what I want to say is that there is a natural identification of this guy with what? With the tangent space of A, of Sn at A. And that's just given by the derivative of F. So the derivative of F, when I restrict to the normal bundle, it's an isomorphism. I've already kind of explained this before, but this is an isomorphism. I mean, yeah, because A is a regular value. Okay, so these, this is M. Yeah, so the normal bundle, it's gonna have, basically by dimension, I guess, there are a few different ways to see this, but you know that the tangent space has to be taken to 0. And so, and df has to be surjective on everything. So this df is a surjection, has to be surjective. But on the other hand, the normal bundle will have dimension complementary to the dimension of Q. And the dimension of Q is n minus m. So the dimension of the normal bundle is going to have to be m. So a surjective map that's of two spaces of the same dimension has to be an isomorphism. So that's one way to justify this. Anyway, this is an isomorphism. And that means it's a natural isomorphism for every x. So that means that now I just have to choose one fixed trivialization of this. I choose my favorite trivialization of this guy. And then that gives me a framing of Q. So I fix one basis here. So I fix. So I fix an oriented basis of TA of Sm, whichever one I want. V1 through Vm. And then dfx inverse of E1, and then dfx inverse of EM will give me the desired basis that trivializes an x. The desired basis of this normal bundle is a basis of nxq. And the other thing to realize is if I change my basis here, if I change my basis of Sm to another oriented basis, then I have a homotopy of bases or an isotopy of bases. And that's going to induce an isotopy of framings. So, like in the framing world, these are the same framings, because usually we think of the framing as a trivialization up to isotopy. So, it's a choice of bases up to isotopy. So it doesn't actually matter which oriented bases I choose for Sm, because I'm going to have equivalent framings, so isotopic framings. Okay? All right. Okay, so here's one remark about this. If n is equal to m, Q will be a collection of points and what's a framing? So framing is going to be the same as a choice of orientation, because if I take a point, the normal bundle to the point is the whole tangent space. And you see that this procedure is going to be exactly the same as how we induce the orientation on the tangent space, of X. So if Q is a collection of points, a framing modulo isotopy is the same as an orientation. I mean, that's already true without even looking at pre-images. So if I take a point, if my submanifold is a point inside of X, what's a framing? A framing is a choice of a basis for the normal space. So if this is X, then the normal bundle is the same as the tangent bundle. It can be identified with the tangent bundle. So a framing will be just a choice of basis there. So modulo isotopy, that's a choice of orientation. So this fact here that the manifold, the pre-image comes with a natural framing, we already knew when n is equal to m. So when n is equal to m, this induced framing is basically the same as the induced orientation, if we think about framings modulo isotopy. Okay? All right, any questions about this? Okay, so I'm almost done today. I just want to say what happens when we homotopy our function. So if the dimension, if m was equal to n, then we know that when you homotope the function, the total number of points are the same if you count them with signs. But what happens if the dimension of the dimension is bigger? Then we're going to have two homotopic functions, and we're going to have two submanifolds. And how are they related? So I guess that's kind of the question. So say that f and g are maps from xn to Sm, and f is homotopic to g. Then what can you say about the pre-image of A and the pre-image like that? How are they related? What's the relationship? Well, instead of defining it, I actually want to construct it with you. It's not so hard to kind of come up with what it needs to be. So, basically, let's choose the homotopy. So let's say F is a homotopy. Homotopy from F to G. And if A is a regular value of F and G, we might as well assume that A is also a regular value of F up to a little perturbation. So, such that F is transverse to A. So what we can do now, we know it's transverse to A and it's transverse to little f and little g. So we can look at the pre-image of A by capital F. So then this guy here is a compact manifold such that the boundary of that, so this is going to be the boundary of G union, the G inverse of A times 1, I guess I should say that. Minus 0 times F inverse of A. So this is kind of very similar to what I constructed at the beginning of the proof of the Thom isomorph, of the Hopf theorem. So what happened, back then, these guys were just points. And I said we can construct a curve whose boundary, in this product manifold, whose boundary was 1 times this and 1 times that. But this is actually true, basically, in higher codimensions, too. So if X is a higher dimensional manifold, then basically what I'm showing is that there is some compact manifold whose boundary is basically the two manifolds G inverse and F inverse of A, but with a minus sign. So this, basically that picture that I drew here, if this is your, say this is your F inverse of A, and this other thing here is G inverse of A. So what this is saying is that if there is a homotopy, then you can find a compact manifold of dimension 1 higher, such that the boundary is exactly G inverse of A and F inverse of A, but with the opposite orientation. So this is actually an equivalence relation of submanifolds, and this is called a cobordism. So that's what I'm going to define now. What is a cobordism? And this generalizes the idea of having the same degree, basically. So definition, two oriented and compact submanifolds Q0 and Q1 are said to be cobordant if there exists an oriented, so usually these without boundary, if there exists an oriented and compact W inside of the product 0, 1 times X, such that the boundary of W is 1 times Q1 minus 0 times Q0. When I say minus, I really mean union with this other one with the opposite orientation. So this is what it means to be cobordant. And sometimes, if Q0 and Q1 have framings eta 0 and eta 1, we could require this cobordism, W, to be framed as well. We may require W, well, let me say the following thing. So if these guys have framings as well, then what can you do? You can look at the normal bundle of W restricted to Q0 and to the boundaries. And it's not hard to see that when you restrict the normal bundle to the boundary, if it's transverse at least, if W is transverse to the boundary of 0, 1 times x, then the normal bundle is canonically identified with the normal bundle of Q0. So, let me draw a picture to kind of convince you that that's true. So, so if I have a cobordism, so here's my cobordism. I'm not drawing x, but this is 0, 1. And if I'm on the normal on the fiber 0, when I look at the normal vector bundle, on the normal bundle of W, basically the normal bundle of W, the extra direction that I get from W is transverse to 0 times x. So that means that there is a canonical identification between the normal bundle of W restricted to Q0 with the normal bundle of Q0. And the same thing, or I should say 0 times Q0. And the normal bundle of W restricted to 1 times Q1 is isomorphic to the normal bundle of Q1. Okay, so that means it makes sense to say to ask whether there's a cobordism that has a framing that coincides with given framings on this guy and on that guy. And if that's the case, then we say that the cobordism is framed. So it's a framed cobordism. So if Q0 and Q1 have framings, and W has a framing that restricts to eta 0 and eta 1, we say that Q0 eta 0 and Q1 eta 1 are framed cobordant. Okay? So I think we've kind of covered a lot of stuff, but I wanted to set this up, and basically the next step would be to show that this cobordism here that you obtain from a homotopy will also have a framing that's kind of given in this exact same way by just identifying the normal space to a fixed tangent space of SM. And therefore, these two, the preimage of A and the preimage of F inverse of A and G inverse of A, are not only cobordant, but they are framed cobordant. And this framed cobordism is the thing that generalizes the degree. So we'll see, basically, yeah, we'll see next time. Next time I'll actually prove the whole theorem and finish the whole construction to prove that, first of all, if two maps are homotopic, then the preimage of a regular value will be framed cobordant. But then vice versa, this framed cobordism class is equivalent. There's a bijection between these framed cobordism classes and the homotopic classes of maps. Okay, so I know this is kind of a lot of content and it's very packed at the beginning of the week, so you have some time to digest it over the course of the week. And then next time, I will kind of start again with this construction. So don't worry too much about it. I'll kind of explain it again next time, and then I'll prove the theorem for the Pontryagin-Thom construction. Okay, so let's stop here.